Imagine looking out the window of your spacecraft and spotting a deep blue world in the distance. With those rich, ocean-like hues, you might think you found a tranquil cosmic paradise, maybe even a second Earth. But the second you open the airlock, the atmosphere reveals its true nature. You are immediately blasted by winds roaring at 5,400 miles per hour, carrying a storm of razor-sharp molten glass. Because those winds move at nearly 7 times the speed of sound, the precipitation ignores the downward pull of gravity. The molten shards fly entirely sideways, shredding anything on the surface in a fraction of a second. These conditions represent a broader pattern of lethal physics, hiding beneath the vibrant colors of the deep cosmos. So why do these distant worlds host weather that seems to completely break our understanding of physics? Extraterrestrial weather functions as a mechanical reaction to a planet's mass, its orbit, and its proximity to its host star. To understand the universe's most hostile environments, we have to decode the 3 distinct physical engines powering them: velocity, temperature gradients, and pressure. Let's look at the beautiful blue planet known as HD 189733b. It is a massive gas giant, roughly 11% wider than our own Jupiter, giving us a baseline for its incredible scale. Astronomers classify this world as a hot Jupiter. It races around its host star in a tight orbit, completing an entire year in just 2.2 Earth days. That orbit bakes the planet at up to 2,200 degrees Fahrenheit. In this heat, silicate clouds, the stuff used to make windows, condense into liquid glass. Moving at 341,000 miles per hour, hurricane winds completely override the trajectory of the falling glass. In an environment ruled by extreme velocity, wind trajectory dictates the weather, turning silicate clouds into a constant barrage of horizontal shrapnel. A nearby neighbor, called WASP 76b, offers an entirely different environment. This gas giant is twice the size of Jupiter, and its atmosphere drops molten metallic rain. Tidally locked, its rotation matches its orbit. The day side permanently bakes at 4,300 degrees Fahrenheit, vaporizing solid iron into gas. 11,200 mile-per-hour winds sweep this iron vapor to the 2,500 degree night side, where it condenses into clouds and drops as molten iron pellets. Extreme thermal gradients manipulate the basic states of matter, taking rigid metals and turning them into active weather systems. We find a unique paradox on Gliese 436b. This is a Neptune-sized exoplanet orbiting a red dwarf star, a ball of burning ice. The surface temperature sits at 820 degrees Fahrenheit, yet water continues to exist in a solid state. The cause of this environment is the planet's immense density and its resulting gravitational pull. Gravity here physically crushes water vapor into a dense crystalline solid known as Ice 7. The mechanical compression is so intense that the ice cannot melt, even at temperatures that would otherwise vaporize it on contact. Planetary pressure dictates the state of matter here, forcing water into a solid crystalline lattice despite the searing heat. Whether it produces sideways glass or burning ice, planetary weather is a physical reflection of a world's orbital mechanics. Looking at these extremes shifts our perspective on our own planet. Earth exists as a fragile, highly improbable anomaly in a hostile universe. A gentle, vertical rain shower of liquid water here on Earth requires a delicate, perfectly tuned balance of physical parameters. Which of these planetary environments sounds the most terrifying to survive? Would you face the sideways glass, the liquid iron rain, or the crushing, burning ice? Let me know down below in the comments. If you enjoyed exploring these cosmic mysteries, subscribe to the channel and like this video. The universe is a wild, beautiful, and inherently deadly place. Stay safe, stay curious,